Welcome back, guys. See you speaking. Today is about the bits and the bytes. What are the multiples or the sub-multiples of the bit? So first of all, I have two messages for you here. So please take your time to read these two messages because I'm going to start right away telling you that the bit as the unit to measure computing data has no sub-multiples. We good? So let's start it. All the multiples and sub-multiples for the units we currently use everywhere, not only in electronics, or the most of them, they have multiples and they have sub-multiples. And everything is based on what we currently use, the mathematical base 10. So when you talk about the amps with the letter A, sometimes we talk about milliamps, even microamps, even nanoamps. So these are sub-multiples. And with respect of the unit, the sub-multiples are represented by the negative powers of 10. Because if you want to write 13 milliamps, you can write them mathematically like 0.013 amps. But it's more convenient to just say 13 times 10 to the negative 3 amps. So both numbers mathematically are equivalent. Now, the units of the 10, actually the unit in our mathematical base 10, when we talk about amps, volts, meters, whatever you have in mind, is like this. Any number at the 0 power is 1. So 10 at the 0 power is 1. This is the unit. Then 10 at the first power, any number at the first power is the number itself, is 10. 10 at the second power is 100. 10 at the third power is 1000. Now, the international unit, let's say if you want to measure the distance in the metric system for the meter, is 1. Technical units still accepted, still used, by the way, in agriculture, is in some countries it is written deca, in some others it's written with a K, but it means 10 times the unit. So when they measure the amount of milk they collect from a cow, they usually say decaliters to measure the amount of milk. But when they collect the amount of milk at the end of the day to put it into the barrels, they prefer to use the 100 because they have a lot of milk. So this is hecto. So these are technical units, not international units, technical units still in use. Okay? The international unit, though, is this one, 10 to the third power, which is 1000. And then you know that this one is the kilo. So you may have kilo, volt, kilometer, kilo, anything you have in mind. Then you have 10 to the sixth, which is the mega. Okay, the mega is 1 million, and 10 to the ninth, which is the giga, which is 1000 times bigger than the mega, and so on. So everything is based on that. Now, what about the bits? This was based on the decimal base. But in our computers and digital equipment, we don't use the decimal base, we use the binary base. So guess what? If we have to establish the multiples of the bit, we're going to start with the powers of 2. Remember, any number at the 0 power is 1. So this is the unit. And we call this unit, when we measure the computing data, We call this the bit. I'm going to write it here. Several powers of the binary 2. To the 11, to the 12, to the 13, to the 14, to the 15. I think I'm going to stop here. And you are going to see very soon why is this relevant. It's relevant because we're going to compare to what we already know to the decimal. So 2 to the first power, remember, any number of the first power is the number itself, is 2. 2 to the second power is 4. So take a look, you already know the pattern. Any next number is the double of the previous one because the mathematical base is not 10 anymore, it's 2. So it's very easy to go like this. I'm just writing them here in a rush, okay? I don't even need to calculate them myself. Don't worry about this because I'm playing with these numbers for so many years. Okay, so these are the numbers. If you want to check any of them with your pocket calculator, you're very welcome. So now, what the engineers tried to find? They tried to find something similar to what we already used in the decimal. What is the first multiple of the unit in the decimal? Is the deca, even if it's a technical one, it's not an international one, but it's 10. So we take a look here on the list we obtained when calculating the powers of 2 in our decimal. What was the closest one we've got here on the list? Is this one. So it was established as the first multiple of the bit, and this was called the byte. Now, we have a little problem in English because both bit and byte, they start with the same letter B. So do yourself a favor, please. And in the technical documentation, you are going to expect to find the lowercase b for the bit and the uppercase B for the byte. Okay? This is how we can make easily the distinction. Then we go further. What was the next multiple after 10? It was 100 in our decimal. But if we take here a look on the list, the closest number to 100 is 128. It's a bit too far away. It's almost 30% higher than 100. So it wasn't considered as a multiple. Then we go further. Is the kilo. The kilo is 1000. But if you go here to see and to watch the powers of 2, oh, you find something which is extremely close to 1000. It's 1024. And this was called the kilo bit. So now, having this thing in mind, I'm going to write it right away here in the bottom of the page. What would be then 1 megabit? So remember, B lowercase is the bit. Is going to be not 1000 like in our decimal 1000 times 1000. It's going to be 1024 times 1024. Okay? So if you quickly do this and you get 1024 times 1024, take a look, you don't get 1 million. You get 1,048,576. Okay? So it's 1,048,576. So it's a bit higher. Okay? But then, some of you may be confused. I'm going to just write here quickly that what is 1 byte? 1 byte, remember about the messages here. One of these messages you can easily read is that 1 byte equals 8 bits. So 1 byte equals 8-bit. So you can make the conversion anytime between the bit and the byte. However, sometimes people are using like the bit, the unit, and some other times they use it like the bytes. Examples. If you want to know the speed of your internet connection, this is given in megabits per second. But if you want to buy a USB stick, it's going to be something like 64 gigabytes. So when do you use the bit? When do you use the bytes? So in order to clarify that, easiest way is to open a very short discussion about communication. There are two basic kinds of communications in electronics: serial communication and parallel communication. I'm going to insist on the serial communication first, because in serial communication, people are saying, oh, it's going to be used only one wire per task. Okay? Examples here are very easy. This is a coaxial cable, old one. It was used in early computer networks, and everybody knows the kind of coaxial cable. And the reason I'm insisting on that, by the way, there are two standard types of coaxial cables. So if I write it here, coaxial cable, the connector we currently used is called BNC. The BNC has several names. I don't want to discuss them now. It's just the name of it, the BNC. And the reason I'm insisting on it, even if it was invented more than 75 years ago, imagine, it was initially invented for the use in military applications, especially on the Navy, is because even today it's still in use. And there are two kinds of such connectors and cables: 50 ohm impedance and 75 ohm impedance. 50 ohms was used in the early computer networks, and 75 is still used today in television. And again, the reason I'm insisting on that is it's still very much in use. If I take a look on all the oscilloscope probes, even if this is a very simple and cheap oscilloscope, it is provided with two such BNC connectors. So it's still in use. Okay? So it's very largely in use. And even here, if I want to get my Kelvin probe, is using 4 such BNC connectors. Okay? 4 such connectors. Then, the one which is going to clarify the functioning of the serial is an old phone. That cable here, there are 2 shiny contacts right here in the top, is simply because inside the cable, there are only 2 pieces of wire. So, 2 pieces of wire. Why is that? Very easy to explain. It's because if I have here, let's say, one handset, and I have here a second one, let's say here is me, here is my pal, here I have the earphone, and here I have the microphone. On the other side is the same, earphone in the top, the microphone in the bottom. Okay? So, in order to communicate, when I'm speaking, the signal from my microphone goes to the earphone. So that's one task. I want to speak. So this is transmission. Notation is TX. And on the other side is reception. Notation is RX. And when I want to hear what the other one has to say, then it's going to be another wire. So here is its transmission, and here is my reception. Okay? So the phone line has, again, remember the shiny contacts here, there are 2, is one for my microphone to the other side on the earphone, and the second one from the other microphone to my earphone. So the phone needs 2 wires. And by the way, this cable here I have, if I'm taking a look, there are 4 shiny contacts. It doesn't mean that's a better phone. And it doesn't mean there is a phone with 4 wires. This cable is made for 2 lines. On the North American continent, by the way, last time the construction standards were updated were somewhere in 1990. And then, since then, the obligation for all the builders is to provide in any house 2 phone lines. I'm talking about the old landlines, even if few people are still using them today. But the builders are obligated to make these wires inside the houses. And it was initially, when the standard was modified around 1990, the Y2 lines, simply because some houses may have required on different floors 2 phone lines, and in some other cases because one line was used for the phone and the other one for the famous fax machine. Okay, so this is the reason why such cables may be provided with 4 wires. And in the world, if you take a look at any outlet for the phone, is provided with 4 wires. But again, not because the phone needs 4, it only needs 2, one for transmission, one for reception, but because the wires in the wall are carrying 2 phone lines. Okay, so that's about, very easy to explain, 1 wire per task. This is called serial communication. Another thing to talk about serial communication is when we talk about what everybody knows, the RJ45 connector, this one, and the famous networking cable Ethernet everybody knows. This one, if you take a look, there are 8 shiny contacts here inside, 8 shiny contacts. But in normal use, I'm going to put them here, 1, 2, 3, 4, 5, 6, 7, 8. If you give them a number, 1, 2, 3, 4, 5, 6, 7, and 8. Actually, in normal situations, only 4 of them are used. 1 and 2, they are for transmission. 3 and 6 are for reception. Okay, so only these 4. And in special situations, you can use the other 4. I don't want to talk about that because it's not the purpose. What is the relationship now between the 4 wires and the serial? This time, because the speed on the networking cable on the Ethernet is much higher than the speed on the phone lines. This is why the phone lines were abandoned practically for internet communication, because the communication was too slow. Is because instead of having 1 wire per task, we have 1 pair of wires per task. So 1 pair here, another pair here. So this is why the communication is still called serial. Another example I have is for this hard drive. If you take a close look on this hard drive here, you are going to find a notation called S80A. And the letter S at the beginning is serial 80A. So serial 80A, I'm going to mention it here. Serial 80A. Okay. And in the back, I have a conversion cable. So from the serial 80A, which is this one, the other side is for the power. Serial 80A is going to enter right here, okay, like this. The communication can be converted into something you already know, the famous USB. This is USB, okay? It's a standard USB. USB, where the meaning is universal, serial, bus. So the word in the middle with the letter S, this one, is for serial. How many wires are in a standard USB 2, for instance, connections? There are 4 wires. How come these 4 wires means serial, because everything here works with electronic components. You need two wires for the power, 5 volts respectively the ground, and how many wires remaining? 2, exactly like the phone line, excepting these ones are called D plus and D minus, but they are equivalent to transmission and reception on the phone line. So universal serial bus is still serial communication. I think I gave you enough examples about that. And remember again, if I'm writing here 500 megabits per second, this is the speed on the internet given to you by your internet provider, by your service provider. All these things together mean what? The information goes bit by bit on the wire, bit by bit. And then we're going to use as unit for the data transmission or data reception the bit or the multiples, which are kilobit, megabit, gigabit, and so on. Okay? What about parallel? Easiest example I can give you, and by the way, I have right here a parallel cable, so I don't even need to explain anything about it, because you can see how many wires they go in parallel to communicate. Okay? So this is parallel communication. Easiest example is what happens between the processor, the microprocessor in your computer, and the memory, the RAM. The microprocessor is a very impatient guy. It does not have enough patience to wait bit by bit to the information to come to it. It's waiting until you assemble a byte and the information is coming in bytes. So when you talk about parallel communication, then instead of sending the information bit by bit, you send the information in a number of bytes. Examples: your Windows, the old Windows on computers still working in the industry sometimes, the Windows 32, and the modern Windows, starting, let's say, Windows 7, is Windows 64. What is the meaning of the 32 and 64? Between the RAM and the processor, there are 32, respectively 64 distinctive lines for inputs and outputs. So this is equivalent to 4 bytes, and this is equivalent to 8 bytes. So all these 8 bytes, imagine, instead of having 40 wires like this one here, is like having 64 wires going at the same time between the processor and the memory and the RAM. Okay? When you buy, let's say, an iPad, you buy an iPad 32 or 64 or 128, by the way, or 256. All these numbers you find here, where are they coming from? From that list. Because all these numbers are actually representing what? The powers of 2, okay? Excepting the 32, 64, 128, 256, they represent the amount of memory inside the iPad. This is respectively in gigabytes, okay? So this is the amount of memory available for your iPad, but the numbers are 32, 64, 128, 256, and the same about any hard drive or memory stick you're going to buy, okay? So standard examples are for your 256, 512, and so on, gigabytes, for your hard drive or for solid state drive. Okay, these are the numbers. Where are they coming from? From the same list, which are the powers of 2. Okay, everything comes from the powers of 2. So short conclusion about that: depending on the type of the communication, for serial, the unit is the bit. For parallel, you can consider for parallel communication is like the unit is the byte. And of course you can convert, because 1 byte is 8 bits. So sometimes you can talk about, let's say, megabits. Some other times you talk about megabytes or gigabytes. So if I want to write it here, 8 megabits is 1 megabyte. Why? Because in each byte you have 8 bits. Okay, 8 bits. See? So that's how it's working. Okay guys, so this was about bits and bytes. Next time we're going to start dealing with logic gates. It's time for logic gates. Don't forget about the 2 messages here. Thank you very much. See you next time. Bye-bye.